So today we will discuss the topic Introduction to Marine Gas Turbine. So we have here learning outcome number 1, describe the feature of gas turbine and explain how the gas turbine is used for. So here, the gas turbine is used for according to their configuration, gas turbine is used for turbojet engine, turboprop engine, turboshaft engine, turbofan engine. So this is all. This engine here is for aircraft. So this gas turbine engine is used also for marine vessels. So there are vessels, especially those vessels, the fast speed vessels like cruise ship. There are also cruise ship that there is installed gas turbine. So there are also Navy ships that the engine is gas turbine. So in power plant also, there are also gas turbine to drive the generator to produce electricity. So that is the application of gas turbine. So here, so it's not responding. Let us proceed to the basic construction of gas turbine. So basic parts and components of a gas turbine. So we'll discuss this one. So it's lagging. So just wait. So introduction. So by the way, gas turbine have been used for the electricity generation. So in the power plant. So in the periods of a peak electricity demand, gas turbines can be started and stopped quickly, enabling them to be brought into service as required to meet energy demands peaks. Small unit sizes and their low thermal efficiency restricted the opportunity for their wider use for electricity generation. So that is in the power plant. So I cannot scroll. So here we have the limitations of gas turbines. They are not self-starting, low efficiency at efficiencies at parts loads, non-reversibility, high rotor speeds, low overall plant efficiency. So to become this efficient, this gas turbine in the power plant will be combined with the gas turbine and steam turbine. So it will add additional 50% of the efficiency if this is combined with the steam turbine. So now we are here in the basic components. So here we have the compressor or the air compressor. The second is burner. The third is combustor. And we have the turbine. So these are the basic components of the gas turbine. So we have here the shaft, the compressor, combustion chamber, and the turbine. So here This is a schematic arrangement of a simple gas turbine in a power plant. So let's say here, this is the turbine. So this is the diagram. So now you have the compressor, the combustion chamber, and the gas turbine. So the gas turbine is coupled to the alternator, which is this one. Also coupled to the motor, starting motor. So here, when this turbine rotates, this alternator produces electricity. So the turbine drives the alternator to produce electricity. So gas turbine, so simple gas turbine plant consists of here the turbine. So these are the components: the compressor, the combustor, and the auxiliary devices such as starting device, so starting system, so low oil pump to supply lubrication to the gas turbine, fuel pump to supply fuel to gas turbine, and the oil system, and the duct system. So duct system is a channel of supplied air. So next, so we don't need to discuss this one because it is already a lot of information for the topic, the learning outcome. So here, by application, so we have learning outcome number 1, the application. So turbine engine is used for aircraft, so jet propulsion, propeller jets. So in stationary, so peak loads unit, standby load unit, and transmission line. So this is base load unit, industrial electricity. This is pertaining to the electricity generation. So here, locomotive, marine. So in the vessel and transport. So in the ship, marine, locomotive, let's say in the train, transport. So by cycle, we have open cycle, closed cycle, and semi-closed cycle. So we don't need to discuss this one. So here, gas turbine are classified by constant pressure combustion gas turbine. We have open cycle and the closed cycle. So there is advantages of the gas turbine. So this one, you just read this one, advantages. And there is also the disadvantages. Advantages. So here we will continue to discuss. So here, a gas turbine power plant layout with auxiliaries. So as I said before, the main components of gas turbine is turbine, compressor, combustor, intercooler, and generator. So we have here the parts. See, it is labeled, the parts here. So it just example number 1 is this one is low pressure compressor. So here, so for identification, so gas turbine. So here the diagram of simple gas turbine. So we have here the compressor, wherein the air is entering, air inlet. And we have here the nozzle supplying fuel. We have here the combustor, wherein the fuel is combusted, or the combustion happen. We have here the hot gas flowing to the turbine blade. So after when the hot gas here flowing here, the turbine blade rotates. So this is connected in the shaft, and the compressor and turbine is connected in the same shaft by the use of coupling. So when this one rotates, this one also rotates, the compressor. So taking suction of air here, and this one, the exhaust gas will exit in this exhaust pipe. Working principle. Working principle of gas turbine. Air is compressed to high pressure by compressor, then fuel and compressed air are mixed in the combustion chamber and ignited. Hot gas are given up which spin the turbine wheels. Gas turbines burns fuel such as oil, natural gas, and pulverized powdered coal. So, if you were asked what are the gas turbines, three main parts, so air compressor, combustion chamber, and turbine. So, this is the picture. Axial compressor, centrifugal compressor. So here, the compressor, here is the inlet of the air. So, and this portion is burner, this portion is turbine, and this portion is nozzle. So this is the combustor. So delivering fuel to the gas turbine. Gas turbine plant, combustion chamber. So in the combustion chamber, the compressed air combines with the fuel, resulting mixture is born. The greater pressure of air, the better the fuel mixture burns. Hot gases, so here in the turbine, hot gases move to a multi-stage turbine. So like in steam turbine, the gas turbine also has the stationary and moving blades. So the stationary blades guide the moving gases to the rotor blades, adjust its velocity. Shaft of the turbine is coupled to a generator. So types of gas turbines: power plants, open cycle gas turbine, and closed cycle gas turbine. So this is open cycle. So remember, in open cycle, you cannot see the heat exchanger here. So you see, in open cycle, only the compressor, combustion chamber, and turbine. So this is open cycle. So methods of improvement of thermal efficiency of open cycle gas turbine plant: regenerating, regenerator, intercooling, and reheating. So here, this is regenerator. So exhaust gas from the turbine carry a large quantity of heat with them since the air temperature is far above the ambient temperature. So they can be used to heat air coming from the compressor, thereby reducing the mass of the fuel supplied in a combustion chamber. So here, regenerator is, so the exhaust gas is being cooled by the heat exchanger. So this one here, heat exchanger. So that is regenerator. So this is the regenerator. So by passing the heat exchanger, so here the exhaust gas is entering here to the heat exchanger. This one is heat exchanger, which is called the regenerator. So now the exhaust gas here is cooled by the use of regenerator. So intercooling, the compressor utilizes major percentage of power developed by the gas turbine. The work required by the compressor can be reduced by compressing the air into two stages and incorporation with intercooler between the two. So here, you have the intercooler here. So low pressure turbine, high pressure turbine, and you have here the turbine. So in between of this low pressure and high pressure turbine, there is a intercooler. So this one. So intercooler. So that is intercooling. So intercooler, this is intercooler. So air inlet here and air out here. Reheating. So if there is an intercooler, because this is a combination of intercooling and reheating. So after passing so here, there is a intercooler here. So there is a intercooler here. So after passing to the compressor, the air is being cooled by the intercooler before entering the high pressure turbine. So after the high pressure turbine, the gas is entering to the reheater. So after the reheater, it is entering to the low pressure turbine, then to the exhaust here. So that is reheating. So we are here now in the closed cycle gas turbine plant. So in a closed cycle gas turbine plant, so you see the difference. So the compression and expansion process remain in the same, but the combustion process is replaced by a constant pressure heat addition process from an external source. So the exhaust process is replaced by a constant pressure heat rejection process to maintain ambient air. So now, here, in the open cycle, there is no, you cannot see the heat exchanger. Now, in the closed cycle, uh, the exhaust here, the exhaust will enter to the heat exchanger here, and then it will be sucked again to the compressor. So unlike in the open cycle, your compressor takes suction from atmosphere. But here, there is a mix of exhaust gas here, or probably this is all exhaust gas that entering through heat exchanger, then back to the compressor as per this diagram. So after the compressor, it will uh, discharge again to the heat exchanger here, then go back again to the turbine. So this is closed cycle. This is closed circuit. So unlike the open cycle, see here, fresh air from the atmosphere is being sucked by the compressor and discharged to the combustion chamber. Then the combustion gas entering to the turbine and the exhaust gas discharged to the atmosphere. So that is the open cycle. But here in the closed cycle, the exhaust gas is not discharged to the atmosphere, but it discharged to the heat exchanger and being sucked again to the compressor and delivers again to the heat exchanger and to the turbine. So this is closed circuit. Closed cycle gas turbine power plant. So you see here, there's an inlet of air here coming from your exhaust, which is passing through the heat exchanger to cool the exhaust gas, and then it will suck again to the compressor, then delivers again to the heat exchanger and to the turbine. So in a closed cycle. So after here, so this is exhaust. After the turbine, so, to power the turbine, so the exhaust here is flowing back to the compressor through the heat exchanger. So a closed gas turbine is a turbine in which air working gas is circulated continuously within the turbine. So that is the closed cycle. Open cycle gas turbines. So open cycle, fresh air being sucked to the compressor, delivered to the combustion chamber, flowing to the combustion gas flowing to the turbine, then the exhaust gas will flow or will be exit to the atmosphere. So merits and demerits, or pros and cons, or advantage and disadvantage of closed loop cycle turbine over open loop cycle turbine. So merits: higher thermal efficiency, reduce size, no contamination, improve transmission, lesser fluid friction, no loss in working medium, greater output, expensive fuel. So this is the merits of merits of the closed loop cycle turbine over the open loop cycle turbine. Demerits: complexity, large amount of cooling water is required, dependent system not economical for vehicles, weight, kilowatt developed is high, requires the use of very large air heater. So that is the demerits. Definition of gas turbine cycles. So this is the efficient system. Gas turbine and steam turbine plants. The combination of gas turbine and steam turbine plants aims at utilizing the heat of exhaust gas from the gas turbine, thus improve the overall plant efficiency. The popular designs are heating feed water with exhaust gas, employing the gases from the supercharged boiler to expand in the gas turbine. So employing the gases, combustion in the air to the steam boiler. So later on, we will see uh, the video. I will show you the video in this system, the combination of gas turbine and steam turbine. So heating of feed water with exhaust gas, blowing the gases as combustion in air in the steam boiler. Combined gas turbine and diesel power plants. So the performance of diesel engine can be improved by combining with the exhaust driven gas turbine. So three combinations: turbocharging, gas generator, and compound engine. Turbocharging, supercharging, gas generator, compound engine. So this is the last slide. So I'll start the recording. So we'll continue with our discussion. So we already discussed the picture of gas turbine and how the gas turbine, or what are the application of, and how gas turbine is used for, or what are the applications. We already discussed the basic construction, basic parts, components of gas turbines. So we'll proceed to the characteristics, functions. So it's not opening yet. So it's disassembling. So we'll proceed to the video. This is already discussed in this here, and also the turbine application. I'll try again. So this is already discussed, the application. So here comes the video. So here we will so we'll see how the gas turbine works. So it's not good. It's not opening right away. So here, it's not playing. So this is gas turbine. So here there is a compressor. See? So if I so here the compressor. So taking air suction, and the air is compressed in this area, this compressor. So there is a so-called combustor, this one. So the combustor here deliver and ignite the fuel, in which the combustion happen inside here in the combustion chamber. So after the combustion happen, it will pass to the blades, the turbine blades, to rotate the turbine blade. This turbine blade is connected to the shaft, and this shaft is also connected to the compressor blade. So this one will rotate together the same speed because they are connected in the same shaft. So after passing here the combustion gases, it will blow the exhaust gas to the atmosphere. So this is uh, for the open cycle gas turbine. But for the closed cycle, the exhaust gas will flow again back to the compressor by the use, but it will pass here with the cooler. So there is cooler here or heat exchanger. This one. So here there is also heat exchanger for closed cycle, but for the open cycle, this component is not found. So there is also high heat cooler here. So here there is also a cooler for the closed cycle. So cooler also. So cooler. So it's hard to write with the mouse. So for the closed cycle, but for the open cycle, there is no heat exchanger found here, which is heat exchanger or cooler. So this is the principle how the turbine gas works, gas turbine works. So here we will compare the working process of the internal combustion engine, the reciprocating engine, will compare to the rotary engine, the turbine engine. So it's not opening. So this one. So it's not. So here, this is a turbine engine, and this is the reciprocating engine, internal combustion engine. So here, this is intake, this is also intake. I cannot say, but this is the comparison of the turbine engine and reciprocating engine, internal combustion engine. So there is also intake, compression, power and exhaust. So here also is intake here, compression, power here, and exhaust here. So it's the same, but this is rotary engine. Application. We'll go to the application. What happened? It's not opening. So this is coal power plant. So this is steam turbine, not gas turbine. So steam turbine here. So there is a boiler, a big boiler, generating steam, and the steam is used to turn the turbine, steam turbine. So and the steam, after exhausted from the steam turbine, it will go to the condenser, and it will suck again, deliver to the boiler, the feed water, and this become boiler water, and it will boil again by the use of this combustion. So this is steam turbine. Steam turbine rotate by the use of steam, and this is connected by coupling to the generator, alternator. So the alternator producing electricity. Here, gas turbine for beginners. We will see this video. It's not opening. No. So just wait.
Two of the most common applications of gas turbines in modern industries are turbogenerators and turbo compressors. I try to approach a gas turbo generator, or GTG, to better feel the subject. Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealPars videos. This way, you never miss another one. In a gas turbine power plant, there's a generator, which is an electrical machine. But to generate electricity, this generator needs a prime mover, which, for my example, is a gas turbine. The gas turbine transforms the chemical energy in the fuel, for example natural gas or similar fuel, into mechanical energy. The mechanical energy generated by the turbine exit shaft is then transferred through a gearbox to the generator's shaft. Now, my generator can create electrical energy. This primitive form of electrical energy normally has a low or medium level of voltage, and to better manage the power loss in transmission lines, this voltage should be increased by step-up transformers. Such transformers give an adequate level of voltage to the electrical energy to be transmitted through the transmission lines and delivered to the grid. After this brief overview of a sample gas turbine application, I'm going to dig down into the gas turbine mechanism in more detail. First, imagine a rocket in which some fuel is going to burn and create a high-pressure exhaust gas. Based on energy conservation law, the chemical energy of the fuel is transformed into mechanical energy in the high-pressure exhaust gas. When a rocket is fired, the thrust of this exhaust gas moves the rocket forward. This amount of rocket science is enough for me. And now, suppose I fixed the rocket body with a robust mechanical structure to prevent its movement. What will happen? The high-pressure exhaust gas should be released, and it will have no way but backward. Now, keep this structure in mind, and imagine I put a set of turbine blades in the path of this high-pressure backfired exhaust. You see that the release of mechanical energy, which is mostly in a linear backward direction, will mostly transform into a kind of rotational movement of the turbine shaft. And so far, I'd say it's a big success. In that, we've transformed the chemical energy of fuel gas into rotational mechanical energy of the turbine shaft. Now, I have a prime mover for my generator in the above power plant example. Also, this prime mover concept can be used in different applications like turbo compressors or the like. Now that I have the basics of gas turbines, let's focus on a modern gas turbine and its components. Most likely, you know about fire triangle or combustion triangle, which illustrates the necessary ingredients of fire or combustion. In other words, fuel, air, and heat. To transform the chemical energy of the fuel gas into mechanical energy, the fuel should be burnt in the combustion chamber of a gas turbine. So I need air and heat added to the fuel. Air is let into the gas turbine through an air intake and mixed with a proper amount of natural gas. The air-gas ratio is determined based on the specific heating value of the gas and quality of the air, amount of moisture, altitude from sea level, and so on. Now, an ignition system steps in and makes the initial sparks, whereby heat is provided. When the fire is established and stabilized in the combustion chamber, the ignition system will be put out of service. The most critical process in normal turbine operation is to manage the combustion and produce a proper amount of high-pressure exhaust gas. This exhaust gas is applied to the turbine blades, and after rotating the turbine shaft, conducted to the exhaust stack. With this quick review of key components of a gas turbine, I think it's time to decrease the altitude and elaborate on the system further. As I mentioned earlier, air is let into the gas turbine through an air intake. The air is prone to contamination or having some unwanted particles which can harm the system and degrade the overall performance. The screening and filtration are basic requirements for incoming air. Also, proper instrumentation is mounted on the air duct to monitor the draft pressure and temperature. In harsh environments, the air might need to be preheated or conditioned. Also, differential pressure monitoring of air filters will warn the turbine operator of filter clogging. The conditioned air is conducted into the turbine air compressor, which is an axial compressor comprised of multi-stages of blades mounted radially on the turbine inlet shaft. The discharge pressure and temperature of the air compressor are monitored to manage the combustion quality at the combustion chamber. Fuel gas is a key factor in the design and operation of a gas turbine. The manufacturers need to know the details of fuel gas, and only based on its characteristics can they guarantee the performance of their gas turbines. Also, the pressure and temperature of fuel gas are monitored during normal operation of a gas turbine. There are different technologies in properly mixing the air and gas and making efficient combustion from manufacturer to manufacturer. Combustion chambers are of some tubular heat-resistant structures, and fuel is usually injected into it from the circumference and at different cross-sectional locations. The temperatures at different locations of the combustion chamber are thoroughly monitored by means of proper sensors like thermocouples. This high-temperature, high-pressure zone in a gas turbine structure is of the highest levels of importance to monitor and control. Also, the technologies used in the design and construction of the combustion chamber are of the topmost ones. Now that the air-gas mixing is well managed and combustion is going on properly, there is plenty of high-pressure, high-temperature exhaust gas generated and should be applied to the gas turbine blades to make turbine exit shaft rotation feasible. At this stage, the high RPM of the gas turbine rotor should be tightly monitored, and based on the load driven by the turbine, the surge of turbine gets the topmost importance for turbine performance and turbine protection. Vibrations, axial and radial, and speeds, both at the air compressor and gas turbine, should be continuously taken into consideration. This was the simplest way to address major parts of gas turbines, and as one of the most sophisticated man-made machines, a gas turbine deserves more elaboration. Also, there are different technologies which some manufacturers use as their proprietary technology, and were not considered in this video. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.
So here we have also here the turbine engine for marine propulsion.
Hi, I'm Tony Wilcoxon of Veracore Power Systems. I'm here today on this beautiful 50-meter vessel to talk a little bit about the Veracore TF50 marine gas turbine propulsion package. This package is on board this vessel with diesel engines on either side of me. This is a combined gas turbine and diesel engine arrangement. We have two diesel engines and the center boost gas turbine for a typical high-speed propulsion package arrangement. The TF50B engine is rated at 5,600 horsepower at its high performance rating. Delivers about 5,000 horsepower depending on the ambient conditions. That's 4,000 kilowatts of shaft power to a water jet or shaft. The gas turbine operates on marine diesel fuel. I think that's an important fact. We're here with diesel engines also on board. All of these engines use the same type of fuel. Veracore is the OEM for the TF50B marine gas turbine, and we sell this complete package to shipyards and navies worldwide, the package being the gas turbine and the main reduction gear. This is for military vessels, commercial vessels, yachts, any vessel where high speed is a requirement and an important criteria. The TF50B is what you see right here. This is the gas turbine. We're mounted to a main reduction gear mounted directly at this flange right here. No other support is required to support the gas turbine. The main reduction gear does that job completely. Output speed of the gas turbine is 16,000 RPM. That speed is reduced by the reduction gear to about 1,000, 1,200, whatever the water jet or prop requires. So gas turbine reduction gear driving a shaft to a water jet or prop. It's a cold end drive gas turbine. That means that the inlet side of the gas turbine is mounted to the reduction gear. You have inlets here, one on each side of the gas turbine. That is where the combustion air enters. The engine breathes free from this engine room, goes through the gas turbine, and here is the exhaust system. Depending on what type of exhaust arrangement, that exhaust can go up, as it does in this boat, or it can go aft over the transom. The TF50 is configured with all the accessories right here on the top. Here's the starter motor for the gas turbine, in this case, a DC electric starter. We also offer two other types of starters, hydraulic and pneumatic, can be configured for your particular ship application. Other accessories, fuel pump, lube pump, control system connection here, all the accessories easily reachable. The gas turbine uses the same conventional marine diesel fuel, so there's no special fuels requirement. Here we are on the bridge. I'd like to show you a little bit about the controls and display and throttle for the gas turbine. You'll note the throttle for the gas turbine is the same as the throttles for the diesel, actuated in the same manner. To perform a start for the gas turbine, several controls right here. Master control arms the system, goes through a few checks. Idle run position switches in the idle position, and simply a pushing of the start button brings the gas turbine up to idle speed. Once it's at idle speed, full power can be applied almost immediately to the gas turbine. The displays here show the two engine speeds, N1 and N2 speed. N1 is the power producer speed of the gas turbine. N2 speed is the output speed. Since we're not underway, N2 will be at 0. N1 will show the idle speed of the gas turbine, and then the speed will increase as we apply power.
So I will stop the video here. So we'll already discuss all this one.